Hey guys, welcome to the video tutorial over a little bit of springs and a little bit of pendulums. So, a couple problems that would be very beneficial for you to know how to work. First problem is going to be a hanging mass type problem. So this is where you've got a spring and it has an initial length which I'll call L1, and let's say it's 10 centimeters. Okay? And let's say that after you attach a mass to this spring, first let's say that we're on Earth. So after you attach a mass, let's say our mass is 500 grams. Let's say it stretches to a new length that we'll call L2, and let's say that it is now 20 centimeters. Okay? And from that, again, assuming that we are on Earth, so here G is 9.8 meters per second squared, I want to know the value of the spring constant K. Alright. Since I make no mention of how the spring oscillates up and down or has a period of blah, 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 you aren't going to use the period of the spring. What you're going to use is Hooke's law. F, and again that's F due to the elasticity of the spring, equal to negative K X, where X is your displacement. That's how far the spring stretched. So, to get how far the spring stretched, you do L2 minus L1. Well, that gives us 10 centimeters. Now, the units on the spring constant K are newtons per meter, so we need to convert that to meters. So centimeters to meters, you divide by 100, so there's 10 hundredths. So this is 0.1 meters. Now, for K, when you are solving for K, you should always get, again, K is newtons per meter, and it is always positive. So, my elastic force, let's just say hypothetically, I asked you to draw a free body diagram for this mass once it reaches equilibrium. Well, for that, all you need to do is just draw some type of black dot to represent the mass. You would need a force going down, obviously representing the force due to gravity, and then you'd need a force going up to represent my elastic force. Now, this once it reaches equilibrium, in other words, it stops bouncing up and down, these two forces are equal but opposite. So we don't know exactly what the force due to elasticity is, but we do because we know what this object's weight is. So once it reaches equilibrium, my elastic force is equal to my weight. In other words, mass times gravity equals negative K X. Well, my mass, again, my mass needs to be in kilograms, so that's 0.5 times G, which we're on Earth, so G is 9.8, equals negative Kx. Now, my X, in other words, in order for my K to be positive, I need a negative value for X. Now think about it. It stretches down 10 centimeters. So my X value is going to be negative 0.1 meters. Those two negatives cancel, and so you've got 0.5 times 9.8, which gives you a value of 4.9, equals, now these two negatives are going to cancel, so I'm going to go K times 0.1. So dividing by 0.1 is like multiplying by 10. So my spring constant is 49 newtons per meter. So that would be an example of like the first part of the problem that you're going to work. The next part, I might tell you, okay, this same setup is moved to a different planet, okay? Planet Keast. okay, with some new value for G. So you've got the exact same setup, same spring, same mass, but now the spring only stretches to a new length of 12 centimeters. So immediately you know, okay, the spring doesn't stretch as much, so I'm going to get a value for G that is different. And I would ask you, what is that value of G? Well, you know that the spring constant isn't going to change. Look right here. This is the key to solving this problem. mg equals negative kx as long as this mass is left at equilibrium. So, the mass doesn't change. The k didn't change, but what did change is my x. I stretched to a new length of 12 centimeters, so it only stretched 2 centimeters. That's going to be negative 0.02, okay, because I need this in meters. My mass is still 0.5, and I'm going to solve for G. So I'm going to plug in my value for K, which is 49, times negative 0.02. Again, those two values cancel, those two negatives cancel, sorry. And so we've got 49 times 0.02, and then taking that and dividing it by 0.5 gives me a value for G of 1.96, and the units on that are always meters per second squared. So that'd be a really good type of problem to know how to do when it came to springs. Now, for pendulums, you have something that's a little different. So let's say we've got a pendulum and it has a length of, let's say, 4 meters. And let's say that it completes, let's say, 1 cycle every 10 seconds. Okay. And from that information alone, I want to know the value of G for whatever planet I'm on. Okay? So, for that, for pendulums, the only equation that we know is the period of the pendulum is equal to 2 pi square root of L over G. G is what we're looking for. You know that L is 4. Now, the period is the time necessary for 1 cycle. In other words, it's seconds over cycles. Frequency is the reciprocal of that. So it is cycles per second. Now, we don't really care so much about frequency when it comes to this equation. Now, I didn't just outright tell you that the period is 10 seconds, but if you think about it, 1 cycle every 10 seconds. Well, the time necessary for 1 cycle is 10 seconds, or seconds over cycle. 10 over 1 is just 10. So that means that 10 equals 2 pi times the square root of 4 over G. And we are to solve for G. So my first step, I'm going to divide by 2 pi. Again, making sure that I put parentheses around 2 pi. So 10 divided by 2, and then pi gives me an answer of 1.59 equals the square root of 4 over G. So last thing I need to do is square both sides. And so 1.59 squared gives me a value of let's say 2.528. And so lastly, that equals 4 over G. And so I can cross multiply here. Whoa, that looks like crap. 2.528 G equals 4. And so divide both sides by 2.528. And that gives me an answer for G of 1.58. Let's say, yeah, 1.58 meters per second squared. So, Again, the only equation that we know for pendulums is this one right here. So if you see a pendulum, you know you're going to use that equation. So study these two problems, and good luck.